Okay, all right, we are recording. Let's jump in. This is our last lecture, really before our review on Thursday. We'll talk a little bit about that. But today it's just going to be kind of a catch-all of error handling technologies, syntax, strategies that you might encounter. Again, when you probably get to working on larger teams or maybe working on commercial software. But these are concepts that you should be generally aware of. Even though the syntax is different in different languages, they're generally flowing in the same kind of way. So we'll go over them to get you familiar with them. Some of this you ideally should have seen in Comp 130 if you took that. So it might be a little bit of review for some of that, but we'll try to dig a little bit deeper as well. And a second look is never a bad idea. So we have an optional lab. We'll go over the optional grading rules here in just a second, but it's just a simple lab on our exception topic today. And then if you're doing these, if you need it, you can do either one or both, homework 8, homework 9 by next Tuesday midnight. That's our, of course, final exam day. So it's kind of a rough day to be doing all that, but you can, in theory, try to tackle one of those that day or before that day. And quiz 8 is out there. It's a practice on 29, 30, and 31. At a minimum, I would suggest you look at it because you might see some questions in there that are going to be on the final, and you'll want to be familiar with those. It's ungraded, so you don't have to feel any stress about it, but you might find it to be a good part of your practice for the final. I think I mentioned this last time. I haven't done this yet, but if you're over 100% for your homework, I know that seems a little unfair. Thank you for everybody who did your bonus stuff, but I gotta set your maximum contribution for homework at 100%. So if you see that happen, you'll probably get an email from me so you are not feeling like you've been cheated out of something. Pretty much all labs and assignments, including optional labs and the 8 and 9, are all kind of due midnight Tuesday. That is so I can spend the rest of the week grading them along with your final exam and everybody else's, my other classes. So sorry to kind of do that to you, put that all on final exam night, but that's kind of how I got to do it to wrap up the semester. Since I know it's kind of confusing, we need 7 grades to contribute to your 35%. So we'll be dropping the 2 lowest of 9 possible homework grades. So most people didn't even really look at potions. That's okay. I just put it out there for folks who maybe got behind. So it's really just going to be 7. So if you skipped 8 and you skipped 9 and you're happy with your 7 grades, then you're good to go. And remember, homework 8 is that threading homework if you're interested in trying to tackle that. There will not be any threading questions on the final exam. So if you don't do your threading homework, it's not like you'll be missing a piece. It's an important piece for sure, just for your general knowledge, but it's not something you have to worry about on your final exam. Again, no threading on the final exam. And you'll be able to verify that this Friday in the practice final exam, which will come out. Also dropping the lowest 5 of 28 lab grades. So you'll have 23 that'll contribute to your final lab grade, 6 graded quizzes, and of course your midterm and final exam. So that's kind of how we're gonna wrap up the semester in terms of the numbers. The practice will be ungraded, so there's no corrected answers given. So you won't really know why, although you will get a grade on the fill in the blank and multiple choice questions. I will not be grading the essay portion of the practice exams. So really, the essay portion of the practice exam is just going to give you a sense of the scale and the kind of type of problem that you're going to have on the final. So I still got to fix it up so it's a little nicer, but you'll see that on Friday at the latest at around noon. And then next Tuesday at 5:40. So not 6:10, 5:40. Please make sure you're here a little bit early. Corrected answers will be given on the following Friday by noon. There will be 25 short answer questions worth 50% of your grade and one large multi-part coding problem, kind of like a mini homework, I guess you could say. Not as much coding as a homework, but kind of on the scale of data structure. Think of, maybe the jigsaw puzzle, right? Or maybe not quite Facebook in terms of all of that roughness, but building something out of multiple classes, plugging in pointers, dealing with dynamic memory allocation, those kinds of things. Again, you'll see a example of that in your practice exam, and it's probably a good one if you have time to try to implement so that you're kind of warmed up for that similar kind of question when it comes on the final. Okay. So by noon, you'll see that example coming out, and hopefully that'll let you know kind of everything you need to know to get ready. For today, quick review, and then we're going to talk about the general topic of error handling. There's a couple nice features that we don't really see and use every time, every day, and especially when we're just coding for ourselves. We'll talk about asserts. What is an assert? That's a useful tool. There's something called a CERR, common error output. It's like the C out for errors. So you might wonder why we'd want to do that. The exit, we'll just talk about a few special aspects of exiting out of your program. Generally, it's of course frowned upon to exit in the middle of your code. Not something you want to really do, but it's good to be familiar with what happens. And then managed or controlled recovery, exception handling. We trip, we want to recover when we're stumbling and not crash. So how do we do that, and where are the situations in which we do that? And that brings us to our try, catch, throw, which is the syntax in C++ for actually recovering from these types of errors. So we'll go through that. It's not a really big topic. The syntax is relatively straightforward. And for advanced students, you should be able to grasp some of the finer points of it that the beginning students probably didn't quite absorb because we just introduced this to them. But the main idea with these exceptions is when you have a bug, if you're not paying attention, basically not trying to catch the bug, we crash. And so we see this all the time when we have crash bugs in our code. We all have been writing code this semester that crashes in different ways. We just might not have been paying attention to the way in which we crash. So once we know the way in which we crash, we have an opportunity to catch the bug, right? And so that's what we really want to do. So just a quick review real quick before we dive into all of that. Remember from our last conversation, we talked about the idea of a class that masquerades as a function. And we just do that in C++ by overloading the parentheses here, okay? So we're making this method, this overloaded method, cause an instance to act as if it's a function. This is really what our Lambda system is based on. So the Lambda system is really building these things behind the scenes for us, okay? So it's something that we can create when we need it, and therefore we can put those lambdas in the middle of nowhere, right? In the middle of or in the middle of a function rather, right? Functions inside of functions is generally not something that C++ allows us to do, okay? So we'll actually look at how we do that here real quick. Remember also function pointers, it's just another kind of pointer, okay? So here is a variable called myfuncvar. It's a pointer. Pointer to what? Pointer to a function. It just has a very strange syntax that we need to know about in order to hold on to a function. And the point of this is that the signature of all these functions needs to really be the same so that we are able to call the function with some argument at any time, okay? So my funcvar10 could go into either the walk or the run, okay? So that's something we talked about last time, really powerful to use. And then our Lambda structure, which as we said before, is built smack on top of our functors, okay? It's just a very, very tight syntax that allows us to do a quick function and either give it a name, right? Or what is more often done, as we said last time, use it as an argument in another function call, okay? So there's some nice Quizlets here that you might want to try if you want to prepare for the final, and that will give you just another way to kind of get ready without having to go through all of your quizzes. Okay, so let's talk about error handling. This is our topic for the day. Types of errors in general that we might encounter when we're coding. We've all kind of seen this stuff, but let's sort of give it a name and summarize them all on one page. We all have made syntax errors, right? We've got commas here instead of semicolons. And so that's going to stop the compiler from building our executable. Our executable is our little bag of zeros and ones that runs only on our iPhone if we compile it for the iPhone, or only on our Intel architecture if we compile C++ for the Intel architecture. A linker error happens when everything compiles fine, but you've got several CPP files like queen.cpp, rook.cpp. They get turned into .o files, and the linker tries to glue them all together. So we had referred to those .o files as compilation units in the past. And so if we can't find all of the connections to all the functions, as we've all experienced before, then we have a linker error. So that is a kind of next step level error. And then, of course, the ones we ran into with Facebook homework, where we have null pointers or divide by zero, or maybe we try to use a bad pointer, a locked pointer, something like that. The last set is, of course, just logic errors, right? We get bad results. That's it, okay? So we need to just obviously think through those problems. The code's not going to help us figure out what those problems are. So these are our tools that we can bring to bear on those. Let's start with the exit and the CERR. They kind of go together, but I've kind of thrown them in the same box for convenience. So in the middle of nowhere, we could just say, hey, if you gave me a null pointer that you want me to, print from, I can't really do anything. So I could do an irresponsible thing and just exit the program. And this status kind of gets passed off to the operating system. So if it wants to, it could try to interpret that in some way, okay? So normally we might exit with a value that indicates a positive result to our program, but that's gonna, give us some clue as to why we erred, okay? Not a very glamorous way to exit the program. It will clean up threads, file pointers, static storage, but we were not gonna trigger our destructors. And so there could be some ramifications if our classes were waiting around to close off a file, or maybe to summarize something before something got shut down, okay? Now, so that's really all there is, right? It's just, it's kind of not the right way to exit the program, but it happens sometimes. CERR is just another form of cout that allows us to kind of separate error messages after the fact. So you're just going to see it by default show up like a cout in your console, but there is a way to run your program so that anything that travels out through the CERR pipe can be pulled off and put, for example, in a separate file. So, for example, if I have an executable called main or main.exe, and I redirect, I say ampersand greater than, right? And there's a little gap here and a gap here, and I give it a file name, all of my error messages are going to just get plowed into this file right here. And these will still go to the screen. So that's kind of a really nice trick, and often one that other systems typically try to include, so that we can separate error dialogue that needs to sort of go to maybe the programmers or the administrators separately from output that maybe is going to a user, okay? And that can be a very useful thing. So that is the CERR. It's common error. It's just as simple as that. And if we don't do this, or we can't do this, for example, there's really no way to easily tell the difference between these two. Okay. So it'll just all look like output on your screen. Okay. So not a really big uh, um, topic. This right here is sort of language you might engage in Linux, right? If you were in the shell in Replit, for example, there are all sorts of things we can do with the inputs and outputs of a particular program that's been compiled like main. And this dot slash here, this is not really part of this class, but that's how I indicate in Linux that that's the folder I wanted to execute in, the current dot folder slash main. So that's really all that extra stuff is there. So if you were using Replit and you kind of wanted to test this out, or any other place where you can get at your compiled executable, just type the name of your executable like main or dot slash main, redirect. So ampersand is for errors, redirect is the greater than symbol into some file. And you should be able to open that file later on and kind of see the stuff that comes out of there, right? This is the stuff that comes out of the error.txt over here, okay? And then everything else will generally show up in your console over here, okay, from the normal couts. Okay, so a handy tool to kind of make your output a little cleaner, but not very complicated, really. The next one is assert. So assert is kind of the way it sounds, comes from the C assert library, but you're asserting a true fact in your code, where it's sort of like, if ever that fact does not end up being true, your program should immediately halt. So let's say suddenly gravity wasn't working, that would be a valuable assert. Like we're going to just say, hey, at this point in my code, there should be gravity, right? Or something like that, that is never going to be wrong. Okay. So one should always equal one, right? So if that ever was not true for some crazy reason, our program would immediately stop right there, because that means something is very, very wrong and we should know about it very early. Similarly, if I assert that false is equivalent to true, and that ever happened, that would halt the program. Now, that program you see right there is going to have normal termination, because those things are not true. Oh, sorry, sorry. I'm asserting that false is equivalent to true, so that would not be true, and so that's going to stop our program right there. Okay. So if this is true, we keep going. If it's not true, we terminate. So sometimes I mangle that one, but that's really what we're doing with those asserts. So normally you kind of do asserts around things you're pretty sure are true, but if you find out they're not true, you want to know about it pretty darn quick, okay? So that's something you put in your code maybe when you're struggling to understand what's going on, right? And it's not something you generally put in your code when you're planning to just ship it out to your customers or your boss for your summer internship, okay? And it's also something you might say, hey, I was going to put some asserts in my code. You might ask your boss and say, hey, is that okay? I'll take them out before we ship the code, but they help me figure out, what's going wrong. And they may say, yeah, that's okay, or maybe that's not a good idea, okay? Now, there's a little trick with these asserts where I can tag on a message. So this is kind of a hack, really. But if I say true and failed in main, that's going to force that message to be printed for that particular assert if it triggers, okay? So really, this is the logic we're testing. You're saying, hey, I'm pretty sure false is equivalent to true, but if it turns out that they're not equivalent, we'll see a little message get printed out. So that is something that people do tend to do using this assert, just so you get a little more information about why your program stopped, because otherwise you might have no idea. It doesn't really help you much. Yes, question. So let's talk about that briefly, because we are an advanced class. So this is going to compare false with true and a string. So a string evaluates in a Boolean sense to true, unless it's a null string or maybe an empty string. So all we're really doing is comparing false with a true over here. But when the program terminates, it's going to spit out the side of the assert that caused the failure. And so that is a sneaky way of forcing it to print out a little message, which is otherwise not possible with the assert. So it is legal in terms of Boolean logic in C++, but it's certainly admittedly a hack in terms of getting that little message to print out on the screen.
Could you put the void function in there?
Man, I don't know if it, well, you, I don't know. I'm not sure what you could throw.
Would it be a compiler?
Yeah, it might be tricky, and there are better ways, but this is one that's quick and dirty, and I've used it on occasion, and we'll use it in class just so you can kind of document what's going on. But everybody's got their own way of actually doing that. So let's just run one of these real quick, just so we see the code here. Let me just kind of make this a little bit bigger. Okay, so here's I'm saying, hey, I'm pretty sure false is equivalent to true, right? So when I run this, it says assertion, false equals true, and in main, I added this to assert failed. So it's saying this is what failed. So we kind of get this little sneaky little message jammed in there, which helps us know where to go in our code and kind of find it. Yeah, that's all. Yeah. So here's another example, right? But here we're going to use our compiler or a pre-compiler, right? So our directives pound define debug. And this is something that happens at software companies for sure. We say, hey, if we're doing debug and we're not shipping the code, then we will set this flag here. And that flag is going to allow the assert to stay in the code before the compiler comes along. So we might call this like scaffolding we would put into our code to really make sure we've tested everything before it goes out the door. But instead of actually changing the code by deleting the assert, we just surround it with the if-def debug and the corresponding end-if, and the pre-compiler will automatically do the work for us. It will come through and tear that code out before it gets compiled. So the important difference there is that that code never reaches our customers, right? It's never going to go out the door. It's never in zeros and ones. It's literally ripped out before the C++ compiler even comes around. So it's a way that some companies use of injecting some somewhat messy looking pre-compiler directives, but they allow you to safely test some things before you ship. And the last thing you do when you ship is undefine the debug, which causes the rest of the stuff to be ripped out. Okay. And some companies will do that in very, very critical sections of the code that are really unstable. So they can really be sure they're safe before, they pull off the scaffolding and send it out for production. Okay. Because having the asserts in there kind of does slow down execution of the code. So you wouldn't want that in a self-driving car or an airplane or a rocket or anything like that, or a drone. Okay. So let's take a look at some of these. So we're going to do a sum of squares function, and we're going to assume that the numbers that we're kind of summing, the vector a and b, are the same size. But if they're not, we're going to put a little error message in there, and we'll use our if-defs to kind of just bring both of those things together. So let's take a look at that one here. And then you can comment out the if-def and see if your assert still runs, okay? So here we go. We've got our include. So what is the library we should include? It's good to just do it once or twice. So we remember C assert, right? Even though the command is assert, it's a C assert. We're going to define the debug so we can use it below. Here is a templated function, a vector of type, let's say int. We don't know, right? Another vector of type int is going to return a same number, right? So it's going to return the sum of this, either as an integer or of a double or whatever that happened to be, okay? So we want to implement an assert that verifies that these things are the same size. And we want to surround it with the if def, okay? So I'm going to say pound if def, if def debug, okay? We will say assert that the size, a dot size, is equivalent to b dot size, okay? And we can put a message that says something like, oops, not the same size, okay? And we could probably do better than that, but we'll just kind of stop right there, okay? And then we have to do our pound end if, because remember our compiler directives, our pre-compiler directives require kind of matching commands there. So there we go. We got our scaffolding. So that should catch that particular error. I'm not saying that's a great example, right? But it says, oops, not the same size, right? So let's see what happened in main. So if we go down in main, we can see these things are actually not the same size, right? So if I were to get rid of these, we should see our error go away, or our cert rather, right? There we go. So now we get our answer, sum of products, which is the right thing there, okay? And then if I wanted to kind of remove my kind of debug code, I could literally just, get rid of that, right? That's one way of doing it. And now our asserts are not there. And I thought right. Oh yeah. So you see that we're no longer catching that error, right? So I may be getting the right answer, I may not, right? So, but certainly we're not catching the error there, okay? So that is really kind of all there is to it, right? Combining these two things together is kind of a helpful use of these two different tools. Okay. Okay. So high points, I think we covered most of this stuff. And these are runtime assertions. So it's not really going to get checked until after everything gets compiled and we start running the code. Okay. So that is kind of one of the key things about that particular kind of assert. Okay. So definitely not something we're going to leave in our production code. Great for when we're sort of testing assumptions, especially if we're experiencing some bugs. Okay. Now, the equivalent kind of cousin to this is the static assert. So this is relatively new. It's in the compiler. You don't need to load any libraries to run a static assert because static asserts happen at compile time. So you might wonder, well, what kinds of things can I really test at compile time that I'd be interested in? So again, our silly example, we could say, hey, at compile time, false, if false is equivalent to true, then we're okay. Otherwise, we've got a compile time assertion here. Okay, so this one should assert and fail. It's going to say, hey, this is not really going to work. The nice thing about these static asserts is we have a more formal way to implement a message here, right? So with these things, I can actually send, I don't have to do a hacky thing to try to, get some kind of message printed out. So let's see if we can kind of trigger this one real quick by clicking into here. Okay, so here's our, I think, assert static in main. I don't even think I really need to do anything here. I should see that I got the assert. Static assert failed, right? A is not equal to 2, okay? So A is equal to 3. So if I, flip the other side and test that, we should get our normal termination, okay? So that's all that one is really about. And we should, at this level of the class, have two kind of ideas about how coding happens. We have the compiling and then the running of the executable, right? I know we've all kind of been hitting the run button in online coding, many of us, but there are really two steps going on there. So a lot of these issues happen in different phases of development. This is at the compile time phase, okay? Now, another example of something you might want to do is your code might be running on lots of different architectures. So let's say you're a phone app developer and you're trying to develop an app or a game that runs on lots and lots of different phones, and you do not want to have a different flavor of code that you have to manage for 20 different phones. So you might want to assert that a particular variable has a certain number of bits, right? So if that is not the case, you might want to fail immediately so that you catch that error, because that could result in some pretty nasty bugs down the line. So this is not an unusual thing to do, especially if you can check maybe graphics card libraries, how much memory do you have to deal with, those kinds of things. So any kind of things we can find out about the hardware we're running on, we could do at compile time and say, uh-oh, this piece of code is really not going to be appropriate for that particular piece of hardware, okay? So that can be a very helpful thing to test as well. Okay. Okay, so those are not really deep topics so far, just extra tools in the toolbox, good to know about. The main thing we want to go into and make sure everybody's familiar with one more time is this idea of exceptions. So we're going to work with these keywords throw, try, and catch, okay? So typical thing is divide by 0. Now there's more than one way to do this, but if we're inside of a function like this and somebody gives us a denominator that's 0, we can print oops, but we should know as C++ developers now that there's no escaping returning an integer. If you don't return an integer, you destabilize your code, probably get a compiler warning or error, and it's a bad situation. So we got to return something, but what is the right thing to return there, right? There's kind of no win solution, because if I return some bad math like 0, right? Clearly 0 is not the right answer when I divide by 0, and I don't want to return infinity. It's just kind of a messy situation, okay? And especially if I bury that divide inside of some other kind of function call, right? So I don't want to pass something back that then propagates the error through subtraction and all these other things, okay? So we could try to come up with something clever like setting a validity flag, via a reference up here. So it's like, uh-oh, this is not valid. I'm going to give you something back, but don't pay attention to it. It's okay, but, not ideal. Because still down in main, if the test is bad, what do we do when we bury that inside of other arguments of other functions? There's, definitely not a great path forward if you're trying to use that divide somewhere else as well. Okay. So it just makes things a lot messier. So the idea behind exceptions is it's a more elegant way to get out from under the returning from a function rules that we have to normally follow. So it's exceptional in terms of we're not going to return from the function. So most people don't realize that when we raise an exception in a function, we don't return from the function. We sort of teleport magically through an entirely different system called exception handling, which is kind of hard to visualize since we kind of have spent so much time thinking about returning. But what this system does, it allows us to sort of move the error handling code to a different part of our code base and a different part of our execution flow, so that it's not all wrapped up inside of our function. We just want to write a little divide function and not have to write all of this code to deal with errors, okay? So we leave the handling of the errors up to whoever called our function. So it's like, hey, I got a real problem here. Don't know what you want me to do about it. I'm just a function, so I'm going to raise an exception and you have to catch it. You being, let's say, main, or you being someplace higher up in the call stack than me, okay? So in order to raise an exception, we say in C++ that we're going to throw it, okay? So some languages like Python, you raise an exception. C++, we throw an exception. And they're both kind of like we're chucking a piece of data, into the transporter beam, and it's going to land somewhere else in our code, and hopefully somebody's going to deal with it so we don't crash. Okay. So that's the catch, right? Somewhere there has to be a catcher for throwing that exception. Okay. And we throw the exception if we think there's going to be a problem, or it could be that our bad code causes the runtime to throw an exception, even if we don't want it to. Like if we try to access a part of a string that doesn't exist, right? We go past the end of the string, we might actually raise an exception, an out of bounds exception. Okay. But being able to catch these things allows us to sort of recover and not crash. So if you're a server, we don't want to crash. If you're a self-driving car, we don't want to crash, right? We need to keep up and running. And that's why we're going to try to catch these exceptions. So let's see how we go about throwing these things. So simple throw is just like it sounds. We'll say, hey, if that pointer is null in main, then I'm going to throw an exception, and I'm going to package up a little message that said, oops, there's a null pointer. So the throw is kind of like a function that can only have one package of data sent along with it. And in this case, it's going to be a string of type const char star. Okay. So it's just a little message that goes out. Okay. So if the pointer is not null, okay, maybe we'll do something else, right? So, but every time we throw something, notice that it has a particular type. So this is a const char type. This is an integer type. So the message or whatever we put in there has its own unique type. Okay. Now this is kind of silly code right here. I don't know why I would be throwing an exception here, but I'm just saying, hey, I'm just, throwing some different exceptions around. Now, by default, if nobody catches this, then we're going to immediately exit the program. We call that an uncaught exception, and you'll probably see that kind of code in some of your output on the screen, especially if you're doing your own compilations. So uncaught exceptions are going to crash the program. They always do. It just so happens that we initiated it here, perhaps for no good reason. We just said, well, I'm just going to throw a tantrum and cause my program to crash. But there's lots of things that might raise an exception or throw an exception that we didn't start. Okay. Let's talk about the catcher here. Okay. So when we throw a value, that exception has a particular type. We're raising that exception, and we're throwing that value back, but just not through the normal return stack. Okay. So if I say, hey, I want you to try something. So try we'll talk about is kind of like a section of our code where we think something might go wrong. So if we think there might be a problem that we can't control, we put it inside of a try block, right? So try, pair of curly braces, and then any kind of situation that raises an exception needs to be caught by a corresponding catch block. Okay, so we need to have a catcher that matches the type of every possible throw. Okay, so if the throw A happens, let's say, then we need a catcher over here very much in parallel with the try. Okay, and if there's a B thrown or type B, whatever that might be, we need a catcher for that as well. So that's how the catchers decide which ball to catch. It depends on the type, which seems kind of crazy. So if there's integers flying around and doubles flying around, the catcher for the doubles is got to have to deal with all the doubles. Okay. And if you miss a particular type of exception that's raised, then you're going to crash your program. Okay. So it seems like a wacky system. So here's how we would look at that. We're looking code. We'd say still pseudocode, but we'll say, hey, if something and something and something, throw, and here's a type of exception. Super simplistic. It's an integer with a value of 1. And over here I can say catch int I. So what I've done here is I've named what I caught. I named the ball that I caught I. So if I want, I can do something about it. I can say, hey, I caught a value of I. and that might give us some information about what was the problem in our code. Here, I did not name the character. I just caught it. So there's not much I can really do other than recover. But I will continue with the program because I caught those exceptions. So we won't crash in that case. Yes.
Can you use auto in catch state?
Ooh, that's a good question.
I feel like the compiler would probably get mad.
Yeah, I think the compiler, I think auto is kind of like syntactic sugar. If it can figure it out by the surrounding syntax at compile time, auto can work. But my guess is it probably won't work in that case. Yep. Yep.
And I see when I'm on like Stack Overflow, I see people writing like catch and then like an official looking error like
Yes.
divide by 0 parentheses like
Yes.
method.
Yes. And we'll talk about that. Believe it or not, well, in theory, all errors have been categorized, but we ourselves can create our own new types of errors. Yeah. But yeah, we'll talk about that because those errors are actually derivatives or inherited from a base class, a base exception class. And we'll look at that here in just a moment. But yeah, no, that is very, very typical. And that's certainly where we're going. But in this case, the first thing to trigger is going to go to the catcher that matches the type, and we'll then skip down to the continuing portion. Okay. So we're not going to kind of do all things. It's like we exit on the first raised exception. We look for a matching catcher, and then we skip to the continuation portion and don't deal with any other catching. Okay. So we maybe never even threw a C, but if we hadn't had this code here, it's possible we might have ended up triggering that exception as well. But we'll never really know because the first one sort of got us out of hot water. Okay. Now, all of these are really, imagine we're in main here. They're all kind of at the same coding level. So it's a relatively straightforward example, but we'll see that we can make things a lot more complicated than just this, okay? But these are kind of two possible paths that we could take in that, okay? And it's just really weird that we continue on. So if this was inside a loop, we would just keep looping. We'd go back, maybe get some data from the user, try something again. Hopefully we didn't crash this time. So there's always a continuation after we catch, okay? So this is kind of a silly graphic, but we could throw any kind of data, right? Including, and this was to Luke's point, including an instance of a class. So if I throw an instance of foo, now we have this open door where we can package up an instance that describes a lot more about what kind of error just happened. So these little data types, string, int, char, are actually not typically what we would do. We'd probably have an instance of a class that is far more intelligible as to what just happened. And maybe it's like, hey, you asked me to divide these two numbers. I couldn't do it. Here, you take them. Like, here, I'm giving them back to you. You go figure out what to do with these things so that, we can continue on. Okay. So we have to have a catcher for every possible raise type that we care about. And so in commercial software companies, when a commercial software company like, a real-time physics company writes a library, they don't worry about how to catch it. They just throw it. They just say, hey, you gave me a bad vector. It has a bunch of zeros. I can't use that in any calculations. I'm going to raise an exception. You figure it out. Okay. Because the policy for how somebody might want to deal with that could differ from company to company if they're using this third-party library. So raising of exceptions is really often done without knowing how they're going to be caught. The catching part is up to maybe a whole other team of people whose job it is to respond to these particular kinds of problems. Okay. So, but it helps in some sense keep our code cleaner because all we have to do is throw or raise that exception and hope someone else catches it. If they don't catch it, then they crash. But they'll get a little message that says, oops, you didn't catch this exception that related to a bad vector or something. Okay. So let's see if we can do this by with our try catch block with our divide by zero. We'll just kind of keep it simple for a little while longer. And remember that the type we throw has got to match our catcher. Oops. So let's take a look at this real quick. Okay, so we have A, B, both zero. We're going to enter some values. We're going to say, if B is really small, then I can't divide that. And I want to throw or raise an exception, right? And so we'll do one of type double, and we'll throw the denominator out there, right? So let's say we'll put a curly brace there, put a curly brace here, and we'll just say throw, oop, row B, right? So it's a double. I think B is a double. Yeah, B is a double. Okay. So our catcher out here. So notice this the structure of this. So we need to try around this whole thing. So even though I'm throwing, if I don't put a try there, I'm going to have some problems. So I start my try block. Okay, and we'll finish my try block here. So that's try. You can see the structure of it. And the weird thing about this try catch is there's no obvious connection between these. It's tempting to put more code between these just to cause trouble, but they're never intended to really be separated. Okay, so it's kind of a weird syntax in C++. So I'll say catch, and I want to catch a double. Okay, and I'll say double B. Okay. So that's what I'm catching. I'll say cout. I caught a double with value equal to B. B. Oops. Okay. And yeah. Okay. So let's see what happens here. Okay. Please enter a numerator 1, 0. Okay. I caught a double with value 0. Okay. Or I could say 1 and 0.00000001. Okay. And then I get scientific notation, right? Okay. So it's not something that's technically wrong, but we forced the issue ourselves. Yes.
You try auto.
Oh yeah, let's do it. Yeah, let's do it. Yeah. Sure. I love that. Let's see what happens. Okay. Yeah, auto parameter not permitted in this context. Yeah.
Okay.
So yeah, it just can't quite figure that out there. Yeah. But actually, if we did int, we would crash, right? We'd get, so I'll say 1 and 0, and it says terminate called after throwing an instance of double. Okay. So that might seem a little familiar to some of us. Like we've probably seen kind of exceptions raised like that and didn't maybe know what that was talking about. Okay. So it seems a little cryptic, but now that we're kind of doing more advanced stuff, we can kind of see exactly what's going on there. Okay. So, but that's the try catch. And let me scale things down so you can see it all, or I'll do it we have it on the slides here, right? All in one place. So you can kind of see it follows our usual structure of indentation. But what we're going to see, except for the way I did that, what we're going to see though, is that this part right here can be pushed off into some buried function. So we can make a function call here, which calls another function, which calls another function. And if we run into a problem way down here, exceptions do not follow the return path. They teleport, all the way over to the first catch they can find. It's a weird thing about them. They're not going to use the return structure of our code. They got to kind of bypass that whole thing. So we'll see that here in just a second. But that's the high level, simple approach to doing that. Okay. So now let's do that inside of our sum of products. So we'll just say, try to implement that inside of the function and see if we actually end up terminating our program. So let's look at the code here real quick. Make that a little bit bigger. Okay, not too big. Okay, so here is our try. So we're going to start out by putting it inside of our sum of products. So we'll throw an exception if A is too small, and we'll send A. Otherwise, we'll send B, right? So we'll say if A dot size is less than B dot size, we will throw A. Okay, so we're literally throwing the vector that is templated type. We don't even know what type it is, right? And then we'll say else if, which is implied, but we could say else if B dot size is less than A dot size, throw B. Okay, and I think that line up, yeah. Okay, and semicolon. Okay, and then we have inside, for the moment, we have our catcher inside of our function, which seems kind of weird, but we're going to leave it there for the moment. Okay, so we'll say catch vector t too small. Okay, and print a message. And we'll say see out the vector that was too small was of size too small, dot size. And we could print out the whole contents of this too. I'm going to just be lazy and not do that. But you could print out all the vector. We're getting the whole vector here, right? So we can do what we want with that. Okay. So let's see if we can do this. There's the compute. That's the answer. And here's our two different sizes. So we should get an exception here, I think. Yeah. So throw an exception. Yeah. Okay. Oh, typo. 38. Thank you. If do else, I'm missing it somewhere, right? Else. Oh, thank you. Right. Else if. Thank you. Long day. There we go. Okay. Did I do it again? Same thing. Else if. Else if this there throw. Right. Gotcha. All right. All right. There we go. Okay. So the vector that was too small was of size 5. So we're throwing that exception. So we kind of see that. We'll do that here too, right? So what we want to do though is kind of move the handling, the catch part out of our function. We don't really want our policy to be inside of our function there. So we're going to kind of move this up to the main level, right? Because that way we're not polluting all of our code. So this is our next level of this is nested exception handling. So here, let's just jump to the chase. So we could do something like this if we wanted to. We could try something which itself has a try and a catch. Right now, you'll notice that I'm throwing an integer here and trying to catch a character. So I did that on purpose because it demonstrates that the try catch mechanism itself is nested. So if we don't catch it immediately at the level we're in, it's going to unwind through its own kind of stack and be caught at the outer catch with the outer try. So although that's really kind of weird, the whole system supports that. So you can be really, really deep inside of something and try to catch it. And if you miss the catch, there could be someone outside of you waiting to still catch it. So it's not like all is lost there. So you can see that our outer try in this kind of very simplified example will actually catch the exception we're raising there. Okay. And we can say, hey, that's the thing that you tossed up there. Okay. So that's what we mean by nested try. And these things can be way far away inside of functions like we were referring to. And that's what we're going to do here next. Okay. So, and we'll try not to get it too complicated because we're just trying to get the idea across here. But in real life, this code can get pretty crazy. And of course, our execution is going to continue down at the bottom there, right? If we're inside of a loop or whatever else, we just pop back up there. Okay. So let's try to have the try catch in main for our sum of products. Okay. So hopefully most of this is written. We don't have to rewrite this stuff all over again. Yes.
Is it only catch, or the 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 code compiler only scan through one file for that catch?
Uh, Good question. No, no, because if you do like out of class methods, right, those are essentially living inside of the class once everything's assembled. So yeah, you could have a team just working on separate files of functions that do that. They they get the no fun job, which is not really that unrealistic. It's like, congratulations, you're on the team. You get to do all the exception handling. It's not. It's kind of maybe how you start out your career. So let's take a look. So we've got our try inside of here. We're going to throw A, throw B. We got our catch. We're going to move this catch block to main. So we're just going to tear this thing out of here. Okay. Hopefully I can do this. So in main, we've got to wrap this in a try block, right? So we're going to say, hey, I don't know quite what's going to happen inside of this function, but I've heard that they raise exceptions. And so I'm going to catch, and I know what kind of vector I have, right? So I'm going to catch an integer, right? I've read their documentation and I heard that if I do something wrong, they're just going to throw the offending vector at me. So I know that's going to be the too small vector, right? So now our too small vector message all happens here. We don't have a return anymore, right? We're just going to have a couple error messages that tell us what's going on, okay? So the moral of the story is, even though the raise is happening deep in this function, or maybe function calling another function, we get the catch out here, okay? So I probably blew my loop here. What did I do wrong? So 47, some products to expect catch before token. Oh, right, I got to take the try out of here as well, right? I don't need the try, okay? Because we took that into main as well. So we just say, so our code just got a lot cleaner, right? We just say, hey, if something's wrong, I'm going to throw a tantrum, right? Let somebody else deal with it. And let's see if I got it that time. Yeah. Okay. Yep. Implement a try, catch some of, yeah, there we go. So that was our catch, right? We had an abort. Okay. So that's really all there is to that. And, I make a big deal of it because it's really easy to assume it's returning from the function in some weird way, but it is just definitely not doing that, right? And that opens up a world of crazy possibilities. So imagine you're 100 levels deep in recursion, solving some really complicated math problem, and you run into a problem, right? How do you get out of it? Well, you teleport. You just, raise an exception and it takes you magically to wherever that problem is handled. And maybe we skip that problem and go on to the next one. Okay. So that's kind of how we end up doing that. Okay. Pretty interesting little system. And a lot of architectures have it, but not all of them. So Arduino, for example, does not have exception handling in this way. It's a really simple processor. It doesn't support that. So it really kind of depends on the sophistication of the processor you're actually dealing with. Okay. But most professional grade, consumer grade processors, iPhones, phones, Androids, obviously the stuff that we have on our desk here, these are all pretty modern and handle that stuff. Okay. Okay, so catch all. So this is just a catch all. So you can actually catch ... if you want. And probably you'll get in trouble with your boss if you do, because it doesn't really tell you anything about what you caught. It just stops execution from crashing. So if you've got a really buggy program and you never want it to crash ever, no matter what, just put a catch ... at the bottom of your main and put everything inside of the try block, and you'll never, ever crash in theory, right? Unless it's really, really bad. Okay. So if you put that first, you'll never catch any of the other more specific catches. Yes.
Can you use that on websites anywhere else
Ha.
for malfeasance?
Actually, there's something called variadic templates that we might. I don't know if we're going to cover it actually, but yeah, there's one other place. There's dots in C++, but it's not the same meaning. I don't. Actually, it might be the same meaning. Yeah, I'll have to look and see. So here's an example: try, run, program, catch, right? So that's a pretty abusive stuff. You'll never crash, but you'll never know why you didn't crash. So somebody's got to go fix that program. So I don't know if I've ever seen anything quite like that in real life. Let's talk about our exception classes, and that'll give us a brief reminder about inheritance, and then we can kind of let you guys go on your way. So because we can throw a class, we could design our own exception class if we wanted to. So that right there is a fully functioning class. Class my exception. It gets a default constructor, so it works. So we can create one of those on the fly and just say throw my exception. And now we're chucking around an instance of the my exception. It doesn't help us much because it doesn't have any data members to tell us anything. But now we could say catch my exception and give it a name if we wanted to try to do something with that instance. And that is the normal way you usually see exception handling. People aren't throwing integers or characters around so much. They're packaging them up in some kind of an instance of a class so that it has some like nice drawers inside where you can store stuff. So for example, it's like, oh, there was a problem when I tried to open the file. Oh, well, what file were we trying to open? Oh, it was such and such a file for reading or writing. Like we can get all that information and kind of go, oh, we got to go fix that in our file handling code, right? Or maybe the file system just hiccuped that day, we just don't know why. So here's an example of a templated custom exception, okay? So it's just saying, hey, I'm going to have a message. I'm going to have a vector of some stuff. And there's my constructor. And here's my constructor initializer list, all that good stuff that we kind of looked at this semester. Okay, so that's how I'm going to pass information around when something happens. Okay, so I'm going to kind of breeze over this one and just show you the solution. But here we can just incorporate this into our code so we have a little more formalized structure for passing richer information around. Okay. So we can package up both offending vectors, right? So let's take a look at this is a modification of it that's kind of custom made for this particular kind of function, 2 vectors and maybe a message, right? And so there we go, right? We just configured it. And then when we throw it, we just say throw my exception T because it's a templated class. And T is coming from our templated function. So that's a pretty cool way of stacking these technologies. So Sum of Products has a T. So we just use that for the creation of an exception of the appropriate type, which is pretty darn cool. And then back in main somewhere, we end up catching that thing, okay? And then we can print out, hey, here's what happened, right? With a little more information and exit if we want to, okay? Or continue as we like, okay? But of course, as was pointed out earlier, these things are nothing magic. And so there is always in C++ a standard set of exceptions to start from, okay? And the expectation is that you use those first, and they come from the std exception class. So there is a class called exception in the std namespace. And so we could just raise a generic exception. Well, first off, we could just say, throw a runtime error, right? We don't know. And it's like, hey, what is that? What is a runtime error? Well, we have to go look it up and see what is the purpose of throwing the runtime error class. This is a descendant of the base class called exception. So there's a class hierarchy of exception types that have been designed over the years. And we're supposed to throw the one that's most appropriate so that it gets caught by people who write these sort of catcher management routines. Okay. So runtime error is kind of generic. I just kind of picked that one out of a box, but we could do that. That's throwing a standard exception type that comes from the base class exception, and its constructor accepts a message, right? That's all it really accepts. So it's just a little bit of a message. So maybe it doesn't do all the fancy things we wanted, but we can kind of get away with that. Okay. So if you, and there's the main, right? So try, catch, runtime error, my inst. And I don't know why that T is in there. I think that's just a typo there. That's supposed to be part of the my inst, little typo. But that's kind of us just using the standard library for that stuff. Okay. Now I can't remember if I had oh, there it is. Yeah. So if we want to go over here, let's just take a look briefly. And Python has the same thing. If you go over to Python, sorry, burning your eyes out there. But here is all of our exceptions, right? Logic error. And then we have subclasses under there. Right? There's something called future error, runtime errors, bad type. And some of these you might notice: bad allocation, bad weak pointer. Some of us might have had that quite possibly when we were working on Facebook. So in theory, they're all here, but we can inherit from them and add more capabilities. And I'm not even sure if I got into all of them here. Yeah, I think I did. Yeah. So yeah, that's really what that library is kind of all about. So if you wanted to derive, again, we'll just kind of breeze over this one. But if you wanted to exercise your kind of understanding of deriving classes one last time, this is how we would do that. We'd say, hey, remember chess, right? I'm going to publicly derive from the STD exception, and I'm going to add our own message, and I'm going to add some vectors to it, but it's still going to be from the base exception class. And you might say, well, why do that? What is the advantage of doing that? Well, I think because the exception that we catch could have a fallback to the base class, and it would still catch our exception because it's from the same class hierarchy. But it would be a better idea to have our very specific catcher above that in main, just in case we have the opportunity to print out more information from our class. But this would work too. It's like, hey, I caught a standard exception. I can't tell you anything else about it. And that would work, right? If we hadn't written this right here. Okay. And so that's a reason why we tend to want to derive from the base class. When people don't derive from the base class, this strategy fails. And people do get a little annoyed. They're like, oh, you raised an exception, but you didn't derive from the base class, so we didn't catch it and it crashed the program, right? So we want this kind of thing to work in a standard situation. And so deriving from those exceptions is probably typically what you would be asked to do, okay? And for sure, every company will have their own kind of style for doing that, and you'll be told how to do that when the time comes, I'm sure. So, okay. Now, one last thing. I keep saying that. I thought we were near the end here, but I think we really are pretty close to the end. This was the most annoying thing that happens when we have to construct something and we're halfway through constructing it, and now we find out we got a problem, right? Well, what do you do in that situation? You don't want to leak memory all over the place. You don't necessarily want to crash the program. So exceptions are a really great way to get out of that problem. You can kind of teleport to another location. And when you do that, you will get relatively good cleanup of things that have already been constructed. So the destructor of your class can get called to clean stuff up. Okay. So let's take a look at an example. So we have a car class here, and there's our constructor, and we're going to give it, we automatically get an engine, but we have an empty vector of wheel instances. So remember, this is a vector that someday will have wheels, but it's immediately got 0 wheels in it right now. So if somebody gives me a negative wheel value, right, I can't really construct the car. I could construct it with no wheels, but I probably want to throw some kind of exception that can be caught. Okay. So, but the nice thing is our engine destructor will get called, right? So this thing got constructed, we're going to throw an exception and the engine destructor will clean up that creation of that data member for us, okay? So that is one advantage to, throwing an exception inside of the constructor there. We get a little bit of help on that cleanup, okay? And so the control is going to jump to the catch. So we won't necessarily see the rest of the car destruct. So this is kind of more advanced than we really want to get into for this class. But the idea is that is another classic place we might want to actually engage that, right? Because otherwise, what do? We can't return, from a class without finishing its construction. Okay. And there's main, right? We try to construct the car. If that didn't work, we do some catching on an int or maybe a special exception type. And we could quit or we could loop around and try it again for some reason, right? Prompt the user for a different number of wheels, whatever it might be. Okay. And that is that. Okay, exceptions and methods. So same kind of thing. So if we overload an operator square brackets, right? And somebody gives us something bad, like in maps or like in strings, right? Strings are not arrays, but they act like arrays. We can raise an exception. So we throw an out of index exception here, right? Or throw an index in this case, right? But we could throw a special out of index exception there if we want, okay? So those are pretty typical things. And we've seen those. I think most of us have seen those kind of exceptions from time to time. So this stuff is there. It's not a lot of information. It is only going to be, I'll confirm actually, I want to double check, but I think you'll see it in quiz 8. You may see a question or two on the final exam just to test your understanding of it. And I think they're going to be pretty basic, right? True, false, kind of like what's an exception definition. So we're not really even going to try to test your understanding of the syntax, just of the concept of exceptions and why we have them, okay? All right. So, and there's some audio explanations there if you want, but probably you'll get enough from the video. So our lab today is optional. That means it'll be dropped if you don't do it. And all you're going to try to do is catch all of the exceptions in main and, just write code to sort of figure out why it's crashing by catching the exception. And then go ahead and uncomment the next one, right? Just take them one at a time. And essentially, your program shouldn't crash because you should catch all of the exceptions that are happening, okay? So I think it'll be self-explanatory if you dig into it and you want to do it. But otherwise, we'll just drop that one, okay? And that is it. So thank you, everybody, for your very good attention. Question up front?
What? What are very
I don't think so, as long as it has a corresponding catch. Yeah, yeah. I think you're okay. Yeah, yeah, it really is. Yeah. All right. Thanks, everybody. Have a good week. And let me know if you have any questions about the final exam. See you on